thank the speakers for. I thank the speaker for being here. So I will first give some news about our weekly seminars that now some of you know very well because it's the 7th edition. So next week we won't have any seminar because there is an online conference on mechanism design, on institution design that will be organized by the University of Klagenfurt. So we thought that maybe some of you would like to go to this virtual meeting. So we put all the information of the website of the COMSOC video seminar. And if you could register, you have to register before if you want to attend to this meeting, and you can then join any session you wish there. So we'll have a break next week. The next week, that is the 19th of June, we'll have the first of our 2 sessions that will be dedicated to the Mexico session, that we call the Mexico session, because at the end of June, there was supposed to be the Social Choice and Welfare meeting in Mexico. And many of us, I hope, would be aiming for Mexico at this time of the year. Unfortunately, as you know now, the situation is not very good in Mexico because as every other country, they now have their peak. So I'm happy we're not there, but still, it's sad that Mexico too has its peak as some other countries. So on the 19th, we'll have Jordi Masso from University Autónoma de Barcelona, which was supposed to be one of the keynote speakers, and we'll have one of colleague from Mexico, Roman Spanks from ITA. We'll have the same arrangements the week after with, let me sing, Leah Tiariv and, Tetsuya Oshino. Okay. What shall I say? Yes, okay, I guess now you know quite well the system. If you have questions during the talk, you can use a chat. Usually you put big question in capital before your question, and then we will answer them. We will answer them during the question time after the talk. If it's a clarification question, sometime we could maybe ask Nisarg to answer it directly, or perhaps somebody in the audience can already answer it, especially because today I think we have some of his co-authors in the audience. What else do I say? I think you all know that we have a virtual coffee break between the 2 sessions. So Dominic will send us in breakout rooms for 10 minutes between the 2 talks. And you are free either to go to to join as a virtual breakout room or just to do something else. And then we will be back 10 minutes later to listen to Péter Biró. So I think we're done. So I think I did not forget anything. So I will ask Nisarg to share his screen. Please, of course, unmute your microphones during the talk and even your camera sometimes. So we are ready now to hear Nisarg Shah, and I will talk about resolving the optimal metric distortion project. So Nisarg, you have 20 minutes. Thank you.
All right, thanks, Vincent. So thanks everyone for joining in, especially for those of you who are submitting to the NeurIPS deadline today and still joined in. All right, so this is joint work with Vasilis Gatzelis, who is an assistant professor at Drexel, and Daniel Halpern, who was an undergrad student at U of T working with me, and is now going to start his PhD at Harvard in the fall, working with Ariel Procacia. So this paper is on resolving a conjecture in this so-called metric distortion framework of voting. So, all right. So let me first introduce the ranked framework of voting that many of you already know about. So we have a set of voters. Here I have 4 voters, 1, 2, 3, and 4. We have a set of candidates. Here I have 3 candidates, 1, 2, and 3. And the voters have ranked preferences over the candidates. So I need to apologize that I'm not using any funny pictures or memes to represent voters and candidates, but in this talk, I really just think it would be easier if I go with abstract names. And these ranked preferences are what's fed into a voter voting rule, which then spits out a winning candidate. In this case, let's say candidate A. And we have centuries of research on social choice theory that tells us how to analyze the performance of these voting rules in terms of axiomatic guarantees, things like strategic proofness, strong monotonicity, or converse consistency. So this framework makes it a bit difficult to compare different voting rules. So in 2006, Prokacha and Rosenshine, using computational perspective, proposed a more quantitative framework to assess the performance of voting rules. In this quantitative framework, we still have the same setup as before. However, these rank preferences are now actually induced by an underlying metric space in which the voters and the candidates lie. So here I've shown you the voters and candidates in a two-dimensional Euclidean metric space, but you can just imagine any underlying metric space over these voters and candidates. And the idea here is that when two people are close in this underlying metric space, then they share very similar ideology. Okay, so this draws on the literature on spatial voting from political science. And the way that this metric space induces the rank preferences is that each voter just looks at all the candidates around him and ranks the candidate by their distance from her. And if there are two candidates that are exactly equidistant from the voter, then the voter is free to break ties any way she wants and rank the candidates. All right, so this metric space is what's inducing this rank preferences, but the voting rule still only sees the rank preferences, not the metric space. So the benefit of the metric space is really to evaluate the winning candidate quantitatively. Okay, so for example, you can just look at the social cost of the winning candidate, which is the total distance that the winning candidate has from all the voters. Okay, and you would want to minimize this social cost as much as possible, seeing only these ranked preferences. All right, so just to recap, we have n voters, m candidates who lie in a metric space, and crucially, the distance function of this metric space satisfies the triangle inequality. And this distance is what's inducing this ranked preference profile, which the voting rule takes as input before outputting a winning candidate. And as I said, you can measure the social cost of each candidate as the sum of its distances from the voter. And because the voting rule doesn't really know the metric space, it may not always output a candidate that has the least social cost. So we need to measure how badly the voting rule performs. So we can look at this approximation ratio. So in the numerator, I have the social cost of the candidate that the voting rule F outputs on a particular instance, seeing only the rank preference profile. And in the denominator, I have the least social cost of any candidate on that instance. So this ratio is the approximation ratio of this voting rule in terms of the social cost on this particular instance. And then you can take the worst case over all possible instances. That's worst case over all metric spaces and all locations where the voters and candidates might lie. So this gives you a number that you can attach to the voting rule. So now that each voting rule comes with a number, you can just directly compare the voting rules and you can ask which voting rule, for example, is the best. Right? So that's a natural question. What is the lowest possible distortion that any voting rule can ever achieve? And here I'm only going to focus on deterministic voting rules for now. I'll talk a bit about randomized voting rules later on. All right, so just to contextualize our result a bit more, let me mention the distortion of some known mechanisms from the literature. And these are not all the results in this line of work, but I'm just presenting some very selected results here. So in the very first paper where Anshulevich et al. Presented this metric distortion framework, they showed that K approval for K more than 2 has pretty bad distortion. It's linear in the number of voters, which is usually very large. Plurality and Boda count do a bit better. They have linear distortion in the number of candidates, which is much smaller. A very recent paper by David Campe this year used LP duality framework to show that ranked pairs and Schuse's rule have distortion that's roughly square root m. And Piotr Skoron and Edith Helkind had a result in 2017 where they showed that STV has roughly logarithmic distortion in the number of candidates. And even back in the very first paper of Anshulevich et al., we already knew that constant distortion is possible to achieve. So Copeland's rule in particular achieves distortion of 5. And for many years after that, it wasn't clear whether this barrier of 5 can be broken at all. And then last year, Ramesh Munagala and his student had this brilliant paper where they proposed a new voting rule that actually achieves a distortion of roughly 4.2. So this raises the obvious question of how much you can even hope to improve over this latest distortion result. And so by now you must be curious as to what the lower bounds are that we know. And there's only basically one lower bound that we know, a simple lower bound of 3 that you can get with just 2 candidates. So imagine this simple scenario where you have half the voters telling you that they like A more than B, and half the voters that like B more than A. And by the way, just to answer Bill's question, no, the voting rule does not know the metric, but we know the metric when we are evaluating the performance of the voting rule. Okay, so we can use the metric, we can try all different metrics, we can see what the voting rule does, and that's how we measure its distortion. All right, so you have half the voters like A more than B and half the voters liking B more than A. And without loss of generality, let's say your rule selects A as the winner. Then you might be faced with this very bad instance where B is actually a good candidate who lies halfway between the two groups of voters, and A is a rather extreme candidate who lies on the other side of one group of voters. And note that this left group of voters only ranked A above B because A is well slightly closer to them than B is, but for the right group of voters, B is much closer to them than A is. So in this case, if you do the math, you'll see that A has social cost that is roughly thrice the social cost of B. Okay, so because your rule selects A, it already has distortion that is as bad as 3, which means that the distortion of any deterministic voting rule can be no better than 3. So the question is, can you get a distortion 3? And the main result of this paper is that we design a new voting rule that actually achieves this distortion of 3. So what I want to do next is I want to present this voting rule to you. But in order to do that, I'll have to take a little bit of a detour, and I have to introduce to you this notion of the so-called domination graph of a candidate. Okay, so this is the notion that we define in this paper, and it goes as follows. So you have these voters, let's go back to this instance, you have these 4 voters here, and you have the rank preferences. And I've highlighted A in the preferences of these voters. And I'm going to again write the same voters here and their same preferences, but on the right-hand side, I'm going to highlight the top choice of each voter in red. And now I want to draw a bipartite graph between the voters on the left and the voters on the right, where I throw an edge from voter I on the left, voter J on the right, if J's top choice is defeated by the candidate A that I have in mind in I's preference ranking. So I want the J's top choice to be defeated by A in I's preference ranking. So let's take an example. Let's look at voter 4 on the right here. His top choice is B. So on the left, I would be looking for all the preference rankings where A defeats B. Okay, so I see that in voter 1, 2, and 3's preference, A defeats B. So I throw an edge from voters 1, 2, and 3 to voter 4 on the right. Similarly, for voter 2, his top choice is C. So I want to look at all the rankings where A defeats C. That would be 1, 3, and 4. So I throw an edge from 1, 3, and 4 on the left to 2 on the right. Okay. And the reason I mention weakly defeats here is because I'll always say that A defeats, so the edges aren't directed. I just sort of mention throw an edge for the purpose of simplicity. The reason I'm mentioning weakly defeats here is because I'm always going to say that A defeats himself. Okay, so in particular for voters 1 and 3 on the right, since A is the top choice, I'm just going to take all the voters on the left and throw an edge to voters 1 and 3 on the right. All right, so what is the use of this domination graph? Let's walk through a thought process. Let's imagine that you are trying to justify selecting A as the winning candidate. And voter 4 now comes to you and complains that, look, my top choice is B. I'm unhappy with your choice, so I want you to switch the winner to B. In that case, since voter 3, for example, has an edge to voter 4 here, you can tell voter 4 that I could switch the winner to B, but then look, voter 3 has an edge to you, which means voter 3 actually prefers A more than your top choice B. So if I do that, voter 3 will be less happy. Now, this is a pretty shitty explanation because voter 4, first of all, doesn't care about voter 3 or what voter 3 wants. Second, it's just too easy, right? You can hold voter 3 up in the air, and any other voter that comes to you complaining, even when voter 2 comes to you and says, I want you to switch to C, you can just present the same voter again as justification, saying that voter 3 likes A better than C, so I'm going to not switch the winner to C. So let's make things a bit difficult for us. Let's say that you can't use the same voter on the left as justification for two different voters on the right that come to you complaining. Okay? So if you have already used voter 3 to justify to voter 4, then you can't use voter 3 again to present a justification to voter 2. Okay? You'll have to find a different voter to justify to voter 2 that A should be the right choice. Okay? So in this case, we are in luck because, for example, you can use voter 4. Voter 4 also prefers A more than C. So you can use voter 4 to give a justification to voter 2. So if you continue along this line of thinking, you will realize that what I'm really looking for is a perfect matching in this graph, right? So that I can take each voter on the right hand side and I can use a unique voter from the left hand side to present a justification to that voter. All right, so just to be honest, I don't really think that this is a good explanation that you want to give out to the voters in the real world. This is just a thought process to understand what this domination graph represents. But it's kind of interesting to me that it also has this kind of this ring of an explainability. All right. So let's say that I want to focus on a domination graph of a candidate that has a perfect matching. But what if I can't find such a candidate? So that's where the key result of this paper comes in. So we prove this ranking matching lemma, which says that no matter how many voters you have, no matter how many candidates you have, and no matter what rank preferences the voters have over the candidates, there will always be at least one candidate whose domination graph has a perfect matching. Okay, so you'll never be out of luck where you can't find a candidate whose domination graph has a perfect matching. So I don't want to walk through the proof of this lemma because this is the main result of the paper. It's quite complex, but what I want to focus on is what you can get once you know that this lemma exists. Yeah. So the first thing that you can do is you can now actually define a voting rule that takes an election as input and outputs a candidate whose domination graph admits a perfect matching. Okay. Now, there might be multiple candidates whose domination graphs have a perfect matching. In that case, you can break ties arbitrarily. It doesn't matter. Okay. And what this next result says is that any such voting rule, no matter how you break those ties, any such voting rule will have the optimal distortion of 3. Okay. So I also don't want to walk through the proof of this distortion result, but I just want to show off a snapshot of this proof here, just to show that this proof is rather short. It's just basically one big equation block. And especially people who have worked on this framework before would be able to recognize that this proof is somewhat shorter than the usual distortion proof, especially given that it settles the optimal distortion conjecture. Okay, so this kind of, to me, speaks to the strength of having this ranking matching lemma, having this perfect matching in the domination graph. All right. So now that we have the result of the paper out of the way, let me tell you about a few other results that we have in the paper. And there are some more results in the paper that if you're interested, you can check out the paper. So one thing that we do is we don't just present the distortion results directly. We actually parameterize them using this alpha decisiveness framework of Anshulevich and Postel from 2016. So what they observed is that several voting rules have bad distortion only because voters are indifferent between their top choice and their second choice, right? So they only merely rank their top choice as top by tie breaking. Right? But in real world, voters aren't that indecisive between their top choice and their second choice. Sometimes voters are quite decisive that they strictly prefer their top choice over their second choice. So in that case, what if you imagine that somebody comes to you, gives you this parameter alpha between 0 and 1, and tells you that I know for sure that each voter I is at least alpha closer to her top choice than to any other candidate. Okay, so the distance that each voter I has from her top choice A is at most alpha times the distance that I has from any other candidate. Now, when alpha is 1, this is not really giving you any more information. Okay, because you already knew that the distance of I from her top choice cannot be any more than the distance of I from her second choice. That is how the rank preferences are induced. But when alpha is less than 1, you are learning something more. So you can hopefully reduce the distortion further. And in particular, I like this framework because of the special case of alpha equal to 0. When alpha is 0, each voter is exactly at her top choice because the distance of I from A must be 0. So this captures the special case of peer selection that has been studied in the voting literature as well. And peer selection is when n people vote over themselves to select a winner. Okay? And it is reasonable to assume that each person would rank herself first and then rank the other n-1 people below. And each person clearly has a distance of 0 from herself. So that's a special case of alpha equal to 0. And what we actually show is that our voting rule has distortion 2 plus alpha. So that means for the special case of peer selection, it actually has distortion 2, not 3. Right? And we also show that even as a function of alpha, this upper bound is pretty much tight. So we show a lower bound that's roughly 2 plus alpha minus 2 divided by the number of candidates. So at least when the number of candidates is large, you can't do better than this bound of 2 plus alpha, regardless of what alpha is. Okay, so let me use the last 5 minutes or so to tell you that I write in the beginning when I presented to you the ranking matching lemma. That's only a special case of the ranking matching lemma. The lemma that we have in the paper is a bit more general than that. Okay? And to present the lemma in its full generality, let me go back to this notion of the domination graph of candidate A. So recall that we had voters on the left, voters on the right, and I threw an edge between a voter on I on the left and a voter J on the right, when J's top choice was defeated by the candidate that I have in mind in I's preference ranking. And then I was seeking a perfect matching in this graph. Okay? Now note that on the right, all I care about is the top choice of the different voters. I don't really care about the rest of the preferences. So let me just ignore them for now and let me just write the top choices. But once I do that, I realize that I don't even care about the voter identities anymore. All I care about is which voters on the left, in which voters preference rankings on the left, A defeats a particular candidate, let's say C. Right? So I can forget about the fact that the vote C was voter 2's top choice. I can just bring the candidates here. So now this is a graph between voters on the left-hand side and candidates on the right-hand side. And each candidate is repeated exactly as many times as the number of times that it appears as the top choice of a voter, which is the plurality score of the candidate. Okay. So now what I can do next is I can actually combine the nodes that are repeated for a candidate, and I can just give that node a bit of weight. Okay, so oops, it should be a nice animation there. Okay, so I combine the two nodes of candidate A and I just call it a node with weight 2. And there are only one nodes of candidates B and C each, so I just call them having weight 1. Okay. Note what happens to the perfect matching that I had before. Now these two red edges that were going to the two different nodes of A, they get squished into going to the single node of A. And this basically mimics the degree constraint that I have on the right hand side here, right? So the weight of the node is essentially going to be the number of edges that are coming into that node. So you can think of these weights as degrees. And on the left hand side, let me just throw in degrees 1 or weights 1 for fun. Okay. So now I have this degree constraint for the voters. I have degree constraints for the candidates. And what I'm doing is I'm selecting a subset of the edges that respect the degree constraints of each node. Okay. And the lemma basically already tells me that such a subset of edges always exists for some candidate. So what we can do is we can actually generalize this to degrees that are not integers, but rather real valued. Once you have real valued degrees, you can't really expect to have a subset of edges. You have to go to something called the fractional perfect matching, but you can essentially write down the same version of the lemma for these more general real valued degree constraints, where for any degree vector P for the voters and any degree vector Q for the candidates, there is always going to be a candidate whose domination graph admits a fractional perfect matching. So I don't want to define what the fractional perfect matching is, but the reason I showed you this general form of the lemma is that this induces not one voting rule, but a family of new voting rules. Right? So you can just set a different degree vector for the voters and a different degree vectors for the candidates, even something as a function of the rank preference profile that you see. And that induces a new voting rule, which then selects a candidate whose domination graph admits a perfect fractional matching respecting those degree constraints. Okay. So what are some other interesting voting rules in this family? Well, we know at least one interesting choice. So we are going to keep the weights of the voters equal as before. But for the candidates, instead of having their weights proportional to their plurality scores, I'm going to make their weights equal as well. Okay? So this is one particular degree constraint. If you write down the Hall's condition for the existence of a fractional perfect matching, you'll see that the candidate A, who is selected by the corresponding rule, has the following very easy to state guarantee. That if you look at any x fraction of the votes for any x, let's say you look at half of the votes or you look at any third of the votes, then in that x fraction of the votes, if you look at where candidate A appears and all the candidates that it weakly defeats in those votes collectively, then it will defeat at least x fraction of the candidates. So if you look at any half of the votes, A will defeat at least half of the candidates. If you look at any third of the votes, A will defeat at least a third of the candidates in those votes. So we think that this is a very interesting guarantee to have, and it's nice to know that a candidate with this guarantee always exists. We don't really know how to make use of this guarantee. We think it may be related to the question of the core for committee selection. So if you are interested in that, we can chat more about it later. Let me just conclude with a few mentions of future work. So the question for the optimal distortion of randomized rules is still open. We do improve the best known upper and lower bounds in this case. So if you're interested in this problem, you should check out the paper. Another thing that would be very interesting is to extend this ranking matching lemma to the case of weak preference orders, or even for the special case of approval preferences. We don't even know what what form the lemma would take in those cases. Another thing to do would be to extend to the lemma in a way where it helps us select a committee of k candidates rather than just selecting a candidate. As I mentioned before, this may have connections to the question of the core for committee selection. And finally, this whole line of work of distortion, which is basically to optimize some underlying cardinal objective function, in this case, the social cost, given only ordinal information about the problem, in this case, the preference rankings, is a very interesting framework that can be applied not only for voting, but for a whole bunch of other problems. So Elliot Enchilevich has actually done this pretty successfully in the past few years. So he has looked at a variety of different problems, for example, the maximum weight matching problem. But you can also apply it to just any other problem that you can think of, say the traveling salesman problem, right? And so this is a very interesting line of research that I believe would produce many interesting papers in the future. All right, so that's it. I'm happy to answer questions.
Thank you very much, Nisarg. I think we can all unmute our microphone and thank Nisarg. Thank you. Can we go to the, can you?
Yeah, so I think I already answered Bill's question first. Okay, then Rita.
There was a lot of questions in this chat, a lot of questions, heated debates about the metrics. So
okay. Okay, I think the next question. Yeah, sorry.
Yeah, I can continue a little bit with that line of questioning. So my initial question was, under what circumstances is your rule decisive?
Oh, yeah, so we don't really know. We don't know under what circumstances there would be a unique candidate that has a perfect matching in its domination graph. But I mean, you can always make the rule decisive by just arbitrarily breaking ties. The distortion result would still hold. Okay.
There was a lot of debates about the metrics, and we have a new question. What if the metric is non-Archimedean?
So the metric is just a pair of a set of points and a distance function over those points that satisfies the triangle inequality. And the voters and candidates are embedded into this metric space, so they might lie at specific points of this metric space, right? And the distance function tells us the distance between these voters and candidates.
Here about a special instance where the metric is generated by having a list of issues, and you compare candidates depending on the number of issues in the ranked order you agree with, and then you have a non-Archimedean metric.
Right. Yeah. So you are right that there are some cases where we may not have a metric that actually satisfies the triangle inequality. Well, there are ways of comparing voters and candidates on a bunch of issues that still satisfies the triangle inequality. For example, a very simple case would be there are a bunch of issues and each voter or candidate either agrees on an issue or disagrees, and you can write 1 or 0. Then you get a vector for each candidate or voter, and then you can just look at a Hamming distance or something like that between these two vectors to define the distance. And this would satisfy the triangle.
That's symmetric. In the Archimedean case, you actually have a stronger inequality than the triangle inequality.
Oh, I see.
This distance between new points is the bound by the maximum of the pairs of distances.
That's true. So you can consider the
stronger
special cases.
Metric, and maybe you can better approximations there.
Right. So that's a great question. I mean, people have actually looked at so many of the papers that I cited. They also look at special cases of metrics. So, for example, they look at one-dimensional metric where the voters and candidates just lie on a single line. They look at two-dimensional metrics. They look at metrics where the voters and candidates I think the candidates lie on like the vertices of a simplex, and then the voters are somewhere in between. So there are all sorts of interesting special cases that you can consider, and these special cases do actually give you a better bound. So I think the next question is, so this question was along the same line. What if we restrict ourselves to graph metrics?
Yes.
I'm just going to look at all the comments with a question colon in front. So Harris asked privately to me, can you say something about the axiomatic properties of the rule? For example, is it converse consistent, etc.? So that's a great question. Actually, a rule is not converse consistent. There is an example where the converse winner does not have a perfect matching in its domination graph. And what we show is that even though a converse consistent rule, even though a converse winner is known to have approximation ratio that's no worse than 3. So even if you, for example, slightly edited a rule to make it converse consistent by just switching to a converse winner whenever it exists, would still have a distortion of 3, but it would no longer have a distortion of 2 plus alpha that we have here. Okay, so we show a lower bound on the distortion of converse consistent rules that is worse than 2 plus alpha. So there are examples where the only converse winner has distortion worse than this for alpha less than 1. So that's something interesting to us. All right, let me bring back the chat window.
Don't think we had a question about uniqueness.
Yeah, okay. Right, so I think the uniqueness question I answered.
Yeah, you answered.
Okay.
I think that's up.
Okay, yeah, that's it. There's a question by Peter after. Okay, so if what if the metric is not okay? Yeah, so that we already discussed. And would it make sense to ask for known voting rules how often they select a perfect matching candidate? Yeah, that actually is a great question. We hadn't thought about that. That would be interesting to answer.
Okay.
Right.
I think you've answered almost all the questions, if I haven't missed anything. So I think we can thank again Nisarg.
Thank you everyone for tuning in.
And this is a time for the virtual coffee break. So Dominic will send us in virtual coffee break rooms where you can discuss for 10 minutes with known or unknown people, or even maybe take a real coffee or real tea, and we will be back in 10 minutes. Thank you.
Hello, Peter. You muted for now.
Yeah, sorry, hi.
Hi, you made it.
Yeah, we just finished the workshop. So we had actually a workshop on this kidney exchange topic because we have a coast action. And
Yes.
exactly today we had scheduled this workshop. Originally, it was to be going to be held in Milan, Italy, but it was cancelled a long time ago.
Yeah. So the first talk went very well.
So how is the schedule? Is it really 20 minutes plus 10 minutes? Or
yes, that's the time. We try not to be too draconic in enforcing that.
Sure.
Because the schedule has a little bit of padding, but should probably aim for 20 minutes, especially if lots of questions are coming in.
But so far, everyone's been good. No criminal convictions yet from time.
It's true. So I have sometimes thought,
You opened the cabinet that contains the handcuffs, but you haven't actually put them on.
Indeed. All right, so just to make sure, do we want to, I'm sure you've done it a lot, but try whether screen sharing works.
Sure. Okay, I just share the screen. And
coming.
It
okay? Looks good. Can you see the chat? So you often at the top of the video, there's like a little zoom bar and there are like options or more.
Yeah.
You can show the chat.
Okay.
Pause. So the downside of seeing the chat is that you might get thrown off by seeing lots of questions. It's better to ignore them. On the other hand, we also like to use it to tell you about the time.
Yeah, sure. I also wanted to ask, I was planning to do some like play asking yes or no. So I remember there was this option. Is it still the case? It's how do you?
That should be there. So in the participants panel, people can click yes or no. So I'm now saying yes.
Okay, where exactly?
If you have to open participants.
Yeah, okay. Yeah, I see it. Okay, it's not available in a normal Zoom, but here this is advanced. Okay. All right. Yes or no. Okay, that's nice. And okay, in that case, I will do this game.
Sounds good. Let's have a look at the breakout rooms. So breakout rooms are very fiddly. I've made them much bigger this time. And that seems to have worked with all rooms having at least some active people. One room with 4. One room with, so all 4 people. That's good. Much better than before.
So is this like randomly generated?
Yeah, it's random assigned. Usually I would pick 10 people per room, and then you'd have several rooms where just one person was active, which is a bit sad. This time and other rooms where 8 people were active. So we had rooms much too large and much too small. So this time I went for 17 people per room.
Okay.
And that seems to have been better.
That's really, this can be quite a nice experiment. Like if you know these people, like how you group them, how you cluster them.
I can't do that. It's too difficult, but yeah, I guess it's a hit-on-it game.
Yeah.
Except people can't actually deviate very much.
Yeah, that's true. And actually,
only I can deviate people.
Yeah, maybe, you know, after 6 months, you check out whether there were any like ideas shared and joint work joint collaboration emerged from these chat rooms. Who knows? There was
by not participating.
Yeah, sure. I mean, maybe it could be also then like you are asking who is happy to, you know, stay in this chat room, and because, you know, some needs to go and have a rest and check the emails and so on. But if somebody is saying that, okay, is happy to stay, then maybe it's more efficient. And then there can be some like sophisticated tools like deciding how to group the people. I mean, this can be random like a Dutch tool, or at least such a more sophisticated where you keep track who used to be in the same room, and like in Dutch tool, I think you are never with the very same people. It's somehow randomized in advance in some clever way. I don't know, but
I think they just have a hat with the names in.
Really?
I'm not sure it's randomized in advance. I think it's randomized every time with no memory.
Okay.
Because sometimes, I mean, you get the same person 4 times.
I was repeatedly put on the table with the same people the last time I was in Dogstool. So.
Okay, so maybe it's in that case it's purely random. Actually, there was a startup. Some Hungarian guys were also involved, but it was based in Cambridge. They call this speed networking. So their suggestion was to run sessions where like a 90-minute session with 6 50-minute chats. It's like speed dating, you know, you chat with someone, but on scientific topics. So in a conference, they organized this speed networking, and they did it in a sophisticated way. So either they surveyed the people, what is their, you know, fields of expertise, what is their interest, and they were looking for kind of complementary pairs. So that was their idea, that putting, you know, complementary pairs together can initiate joint works. And sometimes they did it like senior researchers with junior researchers and like that. And they also, so they started a startup company, and they had an advanced service where they did not ask the participants, but they did like a machine learning. They figured out with data mining, you know, what can be the fields of expertise and the interest of the participants. But anyway, but I think it was just not successful enough, this startup company. But in general, I think this was a nice idea.
This reminds me of the idea of having a co-author who generates completely random ideas, most of which are worthless, but occasionally jog you into an interesting line of thought that wouldn't have happened otherwise.
Now I wonder, who do you have in mind?
I was prepared to not answer that question.
All right, let me recall one song, if I can. I can't.
So are we now in the main room, or this is also just a chat room?
No, this is the main room.
Okay.
Yeah. Interesting. So I can move people to other breakout rooms, but I don't think I can move them out of their breakout room. I'm not all powerful, I thought I was.
So move Vincent around repeatedly. See if he can.
So I think overall, so the rooms are much larger this time. It looks better. We have one room by now, which is empty. But most other rooms seem to have 4 people in them or more.
Is this something that only you can see, or we can see that as well?
No, only me. And it's quite stressful because the variance is so high. So when I make rooms that are large, I worry that some rooms are way too large and too many people are there, so it's not really a breakout room. But so I've always aimed for 10 people, but then you have lots of rooms with just one person in them.
Dominic, let them deviate.
Yeah, I wish we had like a proper hedonic game going here, but I don't think
we
Zoom
can't
can do it.
I mean, it's technically not possible, yeah.
I don't think it is, no. Someone could implement their own video chat service. I think I'll recall people. Oh, people don't want to come back. They're staying in their rooms till the very end. Hello, welcome back, everyone. Hello.
Dominic, is everything okay? Is it running?
Yeah. Oh, do we have one song?
I'm back.
Ah,
So I guess Peter arrived.
Yes, he's
I'm
here.
What I see. Is everybody's back, Peter?
Yep.
So thanks everybody. So I forget to tell you something at the beginning of the session today, is that our next seminar in 2 weeks from now, we will be 1 hour later than usual to be friendly to our North American colleagues. So we'll have the seminar at 4 p.m. European time, and I let you translate in your time zone. What time is it? Okay, so this was just something I forgot to tell you. So our next speaker is Péter Biró, and he will speak about fairness in kidney exchange program. The floor is for you.
Thank you very much for the invitation. Can you hear me okay?
Perfect.
Yes.
All right. Can you see me also? Yeah, okay. Can you see my shirt?
Yes.
Okay, so if you want to, so this is a famous shirt which was kind of prepared for the present for Ulle at the end of COMSOC Cost Action 2016. I still have a few, although, you know, this is very expensive in the black market, but today I will offer 3 pieces. So there will be some game later on. So I hope that you are very excited now. Okay, so fairness in kidney exchange programs. And actually, I also proposed in my abstract that I will tell you a story from 12 years ago, COMSOC 2008, Liverpool. So that talk was about stable exchanges. And since then, we also have some new work on stable exchanges, which kind of related to individual fairness, and some other works on international kidney exchanges. And finally, some overviews on the European kidney exchange programs. So in this talk today, I would like to combine and give a review to you. And as I said, I go back in time. So what is kidney exchange? So 6 weeks ago, Vince started the first seminar about mentioning this topic. So hopefully everybody remembers. But anyway, so we have some patients who need a kidney, and they have a willing donor, but he or she is immunologically incompatible. So these patients can have the opportunity of exchanging these donors with each other. So this is an example of a two-way exchange, a three-way exchange, which should be done simultaneously. So therefore, this should be short. But if there is an altruistic donor, then actually this can be conducted non-simultaneously, and the chains can be much longer or even never-ending. All right, so this was a case from the UK 2007, I think the second one actually. So this lady could not donate directly to her father. So instead she donated to that lady on the right. And in return, her husband was donating back to the father. So in 2007, actually, I just started a research job in Glasgow as a postdoc in the group of Rob Irving and David Melov, and I tried to find a picture from 2007, and I think I managed to find a really good one. So here you can see Rob Irving, and the scenario is really appropriate for him because he really likes to do hiking. So he was a leading figure 80s, 90s on this topic, stable matching problem from algorithmic perspective. His book with Gasfield is really famous. And you can only see the back of David Mello, but you all know David. So his book from 2013 is really the best resource if you want to know more about this topic. So at this picture, he's wearing a shirt which was probably a present from me instead of his usual hips shirt. This is Eric Mcdermott, a PhD student from Wisconsin. And we had several joint papers, and the one at COMSOC was also a joint paper with him. And you can also see Greg, who seems a bit tired after this hiking, but actually he also had a nice work on kidney exchange. As a postdoc, he implemented an IT system for the UK transplant, including integer programming tool. All right, so in 2007, right after I joined the Glasgow computer science department with David, we implemented an algorithm, a graph-based exact algorithm for finding 2- and 3-way exchanges. And then we went down to Bristol and met the coordinators of the UK program. And we managed to impress them because we could solve not just the pairwise, but also the 3-way exchange problem. And from 2008, we had a collaboration. So we always received the real data and we solved them, the optimization. So you can see the details in this paper. From 2009, we switched to integer programming. Now, let me tell you a little bit about the modeling. How can we use graphs to model kidney exchange program? So either we have a two-sided graph where we have the donors and the patients on the other side, the recipients, and the edges represent the compatibilities. But we can also use a directed graph where the nodes are the patient-donor pairs, and we have a directed edge if a donation is possible. We can also have weights or scores, which can represent the quality of the transplant measured in expected lifetime. For instance, 2 can mean 20 years of expected graft survival time. So, and if we are restricting ourselves for pairwise exchanges, then the problem is actually a matching problem in an undirected graph. And the big question is what kind of solution we should look for. Maybe maximize the total lifetime gains by finding a maximum weight solution, or maximizing the number of transplants. So it turns out that actually this is the usual case, maximizing the number of transplants. But the third concept that I would promote also today is stability, where there is no blocking cycle for pairwise exchanges. This means there is no blocking pair. So actually, in that case, the problem is equivalent with the stable roommates problem. Okay, so how complex are these problems? For pairwise exchanges, everything can be done in polynomial time by the Edmonds algorithm or by the algorithm of Rope. So actually, stable solution that is not guaranteed to exist, as we know from the Gale-Shapley paper. So actually, maybe you remember 4 weeks ago, Agnes Che explained this example well in details. So stable solution does not exist, but popular matching does. But then we got that scary bombing. So anyway, a stable solution may not exist, but we can always find one if there exists one. Although problem of minimizing the number of blocking pairs is NP hard. So this was actually my very first international paper with David Menlove and David Abraham. All right, what happens if we have 2- and 3-way exchanges? Then unfortunately everything becomes hard. NP hard is the problem of finding a maximum size or weight solution. So as I already mentioned, for UK transplant, we implemented an exponential time, but still a useful exact algorithm. So our COMSOC paper, 2008 COMSOC paper, was about stable exchanges for 2- and 3-way cycles. And that is also a hard problem, as we proved. And actually, so let me go back to COMSOC 2008. This was the call. Stable matchings and kidney exchange were not mentioned in the call. And actually, I read, you know, the writing of Ullem, and I became absolutely sure that matching papers should belong to this topic. So I submitted our paper and it was accepted, but this was the only paper at that time. So I thought that actually I should maybe try to promote a bit more, you know, this area, stable matchings and kidney exchange. So this was my plan for the talk. The first part, I was trying to argue that stable matching problems should really belong to COMSOC. And then I was planning to give an introduction to kidney exchanges, and finally just the results of the paper. But this was planned for 30 minutes. And unfortunately, my grandma died a week before the conference, and I had to go home to Hungary for the funeral. So in fact, I just arrived the last day, the lunch break. So I could only attend the last 2 sessions. Actually, it was probably Harris's talk that I heard first. And at that point, I realized that all the talks are 20 minutes. So I had a break to adjust my talk. And so what I did, you know, I had to leave the third. So I decided to just drop the last part. So that was quite a strange presentation. So I thought that today maybe I will just, you know, tell you what I missed to tell you 5 years ago. No, indeed, at least for one side. So this was a slide actually from 5 years ago that please let me show you now. So this was the gadget where the first gadget we could find, and the smallest, where stable matching does not exist. Furthermore, this is a so-called tripartite graph, which is also called as the cyclic 3D matching problem, where we have men, women, and dogs, or maybe cats. The literature is a bit divided, dogs and cats. Anyway, we are looking for families, stable families. And the men, they only care about the woman. The women, they only care about the dogs. And the dogs, they only care about the men in the family. Now, this was a long open problem since the book of Donald Knuth from '76, whether there exists always a stable matching, how they look like, whether we can find them efficiently. And actually, this example shows that a stable solution might not exist because, you know, we have 9 inner players and at least one is uncovered, and that one will create a blocking family. So that's very trivial. But actually, the question still remained open whether for complete lists, this problem is always solvable, whether there exists always a stable solution. So, and actually this was open for a long, long time still, until last year. And now I will propose a vote here that I could not have done in 2008 in my COMSOC talk. So now you can vote. What do you think? Actually, the answer was also not known that time. So what do you think? Whether there is always exists a stable solution for complete lists or not? So I give you like 20 seconds to think a little bit. And in the meantime, I just tell you that obviously this 3D matching problem is a special case of the stable exchange problem for kidney exchange. And therefore the MP hardness that we proved is obvious. If we prove it for this restricted case, then the general case is also MP hard. So how can I see the results? Participants, yes and no's. More yeses than no's, about the same yeses and no's, because you know
22 yes and 19 no.
Wow, okay. I was actually also not sure what will be the final results, but last year it turned out that the answer is actually no. And actually they used our gadget, they extended our gadget, and that's how they could prove the hardness. It's still not clear from that paper what is the boundary. So you see that in our gadget we have 3 × 6 agents, and there were proofs for 3 × 5 agents. So I'm not sure how large was the first gadget with no stable solution, but most probably this is still an open question. What is the smallest gadget with no stable solution? All right, so this was a slide from that talk that I missed to give in 2008. And actually, let me also just finish the story by 2 comments I received right after the talk. So first of all, I remember that Ulla told me that it was the very first time we met. He said that, wow, you sacrifice your talk just to promote that stable matching problem should belong to COMSOC. And yes, I did that, but it was not really my intention originally. I just told you the story. So it was just a quick decision before the talk. Otherwise, I wanted to include obviously also the results of the paper. But anyway, and there was another comment as well by Thomas Sandholm, and that's more related to the talk that I'm going to give today. So he said that stability is an interesting concept, but it's not considered in the current applications, and it will never be, because social welfare is always more important than for the planners than, you know, individual fairness, let's say. And yes, actually, I must admit that the last 12 years, I haven't seen any kidney exchange program using stability as the main solution concept. Anyway, let me show you how the European programs are working. We have a cost action on kidney exchanges chaired by David Merlin, and actually I was asked to lead the first working group to survey what is happening in Europe. We did a very comprehensive survey, and based on that, we have a handbook and publication describing the European practices. So let me just tell that you know, there are at least 10 countries with operating kidney exchange programs in Europe. UK is the largest, the Dutch is the oldest, and the Spanish is the second largest. Okay, and I will probably skip these graphs. And also this table, there are many information. We had like 100 questions in this survey, and you can read it in the handbook and the publication. And since this is a video, you can also just pause it and look it if you are interested. But otherwise, let me tell that there are big variances across Europe. And in a second handbook, which was published in, the survey was published in IJOR, we also we focused on the optimization aspects. And we collected what kind of optimization criteria the countries are using. And indeed, the maximum size solution, so maximizing the number of transplants, was the main objective everywhere. So Thomas was right. However, there are also many considerations, criteria regarding the quality of the transplants. So what are these criteria? Age of the donor matters a lot, for sure. You know, the younger, the better. And antigen match matters also a lot. And so these charts are from actually from the website of National Kidney Registry, which is the largest program in the US. And they try to give incentive to the compatible pairs actually to join the kidney exchange pool in the US. And compatible pairs are actually included also in many European programs, also in the UK. And in the UK also, they offer this option to them and everybody else to give age limits and thresholds also for the age-aligned matching. So the two main factors for quality, it's possible to give thresholds. So you are not accepting a too old patient. You are not accepting a donor. Sorry, you are not accepting a donor with whom the age-aligned matching is too bad. And there is also an option of accepting or not an ABO incompatible transplant. So in fact, what my understanding is that this option of putting thresholds can actually make the solution much closer to be stable, especially if we imagine that these thresholds can be iteratively lowered. All right, so the applications are actually very complex, and I believe that there are more and more considerations to consider the quality, and more and more individually fairness options. Let me finish also this table. You know, there is this theoretical case of unbounded exchanges. Although for instance, in Prague, there is a quite brave surgeon who likes to do 6-7 day exchanges, but usually it's not realistic. But for chains, actually, this is also possible to have unbounded chains. So what is the complexity of finding unbounded solutions? Surprisingly, this is polynomial time for maximum weight, maximized solution. And now here comes the question where you can get some t-shirts. So what do you think? What about stable exchanges if we have no bands on the cycle lengths? So I will ask you to put in the chat some names. Okay, so everyone can put one name, and if your name is correct, you will get a t-shirt. I mean the 3 first candidates. So these names should be the famous researchers who gave a solution for stable exchanges for unbounded case, which is also called as the housing market. So who are these famous people who solved the case of housing markets, stable exchanges of unbounded lengths? Let me check the chat box whether there are good names. Yeah. Gail, Scarf, and Shapley. I see all the 3 names. I will track down later on. Okay, so I saw all the 3 names. So let me just tell you that this is indeed the paper of Shapley and Scarf, where the algorithm was the top trading cycle algorithm by David Gale. So it's a bit strange that he was the author of the main algorithm and never became a co-author. So I think it's not fair. Actually, in our next paper that I will present, we call this as the Gale-Shapley-Scarf model. All right, so, and actually this model was proposed in the very first famous paper, at least in the economics literature, by Roth, Sonmez, and Unven for kidney exchanges, so unbounded stable exchanges. Okay, what can we know about stable exchanges? So here, let me just mention two papers we worked on recently. One is with Portuguese colleagues on finding stable exchanges of bounded lengths with integer programming techniques. And we are doing simulations and we check, you know, how likely to exist a stable or strongly stable exchange. And we are measuring also the size versus stability trade-off. And the other paper is very, very new. It's not even written. So where here we prove for unbounded case, this so-called respecting improvement property. And now this is the very first time we are speaking about that. And we would like to check whether this result is already known or not. So the result is the following. If somebody brings a better donor, meaning younger or more compatible, like blood type O instead of A, then in the unique strongly stable solution or strong core solution obtained by the TTC algorithm, she must receive an exchange donor at least as good as before. So if you are bringing a better donor, you are guaranteed to get a better exchange partner. So this is a very, very important piece, I think. And we were surprised not to find it anywhere in the literature, but maybe we are wrong and just don't know the literature well enough. So there are some papers on school choice where actually they show that the TTC is not satisfying this property, but in that context, the TTC is different. It's with capacities. But in this classical housing market, it seems perfectly working, this property. And I think it's a really important property. In other words, you can imagine that in most of the European programs, this property is violated. So you are bringing a younger donor and yet you are getting a worse exchange partner. So this is, I think, a very concerning unfairness. All right, let me move on. So I will be very interested to see the questions and the chats, whether anybody knows these results. But let me move on. So I also wanted to speak about international kidney exchanges, and let me speak at least 5 minutes. Do I still have 5 minutes?
Not really, but well.
All right. Okay, just please give me just 5 minutes. So international kidney exchanges, these are so interesting. So there are many programs in Europe for deceased organ sharing, Eurotransplant, Scandia Transplant, and now there are also some new programs for exchanging living donors across countries. So the CHEV was the first documented case between Austria and Czech Republic, and Tommy just announced last year that the Swedish program joined also with the Danish and Norwegian program, so through Scandia Transplant. So he was one of the main guy behind this design. And okay, what's the main concern? So imagine that here we have two patient pairs in Portugal and they could do an exchange, but there are two others in Spain and you could do a three-way exchange. Okay, so what would be the good solution? So if we don't want to give up optimality, we should do the three-way exchange, but we feel that actually this is not fair for Portugal. So let me move a little bit faster. So in the next round, if there is this situation that Italy can exchange with Portuguese or a Spanish pair, if Portugal sacrificed a transplant in the previous round, maybe it's fair to give this transplant to them and choose a matching accordingly. So I won't have time to describe the details. This so-called compensation scheme was proposed by Xenia Klimentova and Ana Viana and the Portuguese colleagues. And we also had some follow-up papers. And actually, I just wanted to say that this is quite different from what has been described about multi-hospital kidney exchanges in the US mostly. And here are the big differences. So in Europe, reporting full pools from the countries is kind of basic assumption, while in the US, and all of these papers are mostly about how to give incentive to the hospitals to give full reports. Now, in Europe, we have quarterly runs, while in the US, they do online matching basically, because they are competing programs, they cannot wait. And also the pool compositions are much different in Europe across countries, I think, than in the US. And also, so in the solution by Klimentova and co-authors, they propose a compensation scheme based on country valuations, while in the US, at least National Kidney Registry is working with a credit-based system based on pair valuations. Okay, so I don't have much time to explain that, but let me just say that we had these new papers, and you are very welcome to check out the details. Essentially, we are doing simulations to test what is the effects of such policies of using compensation schemes. And at the moment, actually, as part of the cost action on kidney exchange, we are working also on a simulator together with colleagues. And hopefully we can test also some real data and in the next few months. All right, so let me just finish here. And this is the last slide. This is a picture about a meeting we had with the research group. We have this mechanism design research group supported by the Hungarian Academy of Sciences. And we will have a big event next year, postponed from this year. Hopefully by next year, everything will be calm and open. And I hope that many of you will come to Budapest to participate in this World Congress on game theory and the co-located EC conference that we organize with the research group. Okay, thanks for listening, and I'm looking forward to your questions.
So, we have a few questions in the chat, maybe from the beginning. Oops. No, sorry, this is the question before the
okay, so
I have to go after the break. You have to go in the chat before Trisha.
Okay, let me go to the very beginning.
But stop before the coffee break, because otherwise you will go up to the previous questions.
So is UK still part of Europe? Okay.
Below.
Okay, so yeah, it's a good point that indeed, why do we care about blocking coalitions? Presumably they are not able to recognize each other. And I think this was also mentioned by Thomas 12 years ago. So actually there are some alternative platforms they can try. In Hungary, they started to organize Facebook groups to find partners when now the Hungarian Blood and Transplant Organization took over. But anyways, the other reason is that you can also imagine that actually these patient donor pairs can belong to one hospital who would block, or one country. So also this can be an issue that these hospitals or countries can recognize their patient donor pairs could improve already within the hospital or within the country. So that can be also a reason to avoid blocking pairs. But it's more about fairness, I would say. Like, if you are guaranteed to get the best kidney exchange donor through a stable solution, So this respecting improvement property is exactly such guarantee, no matter, so you are guaranteed to get the best possible exchange donor, so you don't have incentive to, I don't know. So you get the right incentive if you have your old, I don't know, father or your younger brother. If you bring your young brother, you are bringing a very valuable donor. You kind of deserve that you also get a good donor. I think its fairness concept is quite relevant. All right, let me move
There's
to
a question by
yeah.
Gerzik. Would stability possibly be considered from a legal liability perspective? Say, the patients might choose an algorithm that matches to the bad option if there's a better match they could have received?
Yeah, so at the moment, there are no legal issues of that sort, I believe. You know, the reason why the number of transplant is maximized is very natural, because that's what the coordinators believe, the decision makers believe is the right thing. But as I mentioned, there is this possibility of having thresholds. Either the patients or, you know, advised by the medical doctors, they can set thresholds. And indeed, in the US also, even if they don't set thresholds, they just, you know, turn down the offers which are not good enough. So in the UNO scheme, 90% of the offered exchanges are turned down, either because of incompatibility or by quality reasons. So if you are guaranteed to get the best possible in a stable solution, I think this can be also kind of this issue of setting the thresholds can be maybe relaxed.
So we have four more questions at the end of the chat, so maybe we should stop questions if you want to answer all of them.
Sure.
So at the end of the chat, there was a question by Aziz Aris. Is the compensation based on the Shapley value of the underlying matching game?
Yeah, so there were 3 papers. I had no time to tell even the main results, but our AMAS paper was about pairwise exchanges only. So that was a theoretical paper, and we were focusing on the core of the solution. In the new paper we had with the Portuguese colleagues, and there is also a PhD student in our group who visited Porto for 4 months. So he was actually the main author. So he tested the Shapley value for the compensation scheme, and for a realistic scenario, so with 2- and 3-way exchanges, and yes, indeed, this is the Shapley value for the underlying matching game. So the value of a country is the number of transplants they can get in that solution, and the value of a coalition is the number of transplants the set of countries can make together. So that's how we define the values for the coalitions. And yes, the Shapley value is one possibility, the core is the other, or nucleus, whatever. And it's quite interesting to see that the compensation schemes are working differently based on, you know, the fairness concept, solution concept selected.
Okay, well, I will take a few of the questions. Maybe if there are more questions, we can stay a little bit longer for those who wish to. Dominic, no? No, you're busy, you want to stop? Okay, no, yeah, Dominic says no, okay.
So you can always just, we can always just close the recordings and everything, and I'm very happy to, you know, answer all the questions, or whoever wants to chat with me. I'm very happy to answer the questions, and for sure I will check who gave the right answers. So for the t-shirts, I need to know, but I would say that please come next year to Budapest and I will give you the t-shirts. Okay, so but I will check out who gave the right answers. Okay, some other
Okay,
questions?
maybe one, two more questions, maybe. Is there any mechanism in which each patient can bring more than one donors?
So in the applications, usually they can have more than one donors, but only one will be used. Okay, so in most of the European applications, it's possible to register multiple donors. And in fact, the respecting improvement property is also important here. If you register not just your one donor, not just your brother, but also your father or vice versa, then in the current programs where the size is maximized as a first priority, you can get a worst exchange donor because of that. You register the second willing donor. But if we use the stable solution, this can never happen because the more options you offer, then the preferences of the other recipients can just improve about you because you have more options, and therefore the solution can only be better for you. So that's why it's also very important that for this reason, this is a good point.
Another question I missed, is there other application of chain exchanges other than kidney?
Sure, sure. So there are many papers. Actually, there was an old application of exchanging old shoes after the Second World War. I think that was the first one. You can have a look at the blog of Aeroth, Market Design Blog. There are many, many examples. Time exchange is actually, there were two recent papers where time banks, you offer your time, maybe you offer, I don't know, 4 hours of co-repetition in maths, and in return you get, I don't know, 2 hours French lesson and 1 hour of haircutting and so on. So you can exchange services. So some properties we are losing if we have capacities, if we are exchanging multiple goods. So we have a new paper also with Philippe Klein and Sylvia Papai, but there are some other papers as well. So exchange problems, and also exchange of votes in this community. I think this is also very, very interesting topic. I was actually thinking, you know, in the Hungarian last election, where again the government won with 2/3 majority, although they barely had a majority according to the number of votes. But since they were united and the opposition were fragmented, they lost. So I was thinking that, oh, with a vote exchange scheme, the opposition could have actually win, but this should be designed very carefully to give the right incentives to the parties. So actually exchanging votes, I think this could be also a very nice application.
Okay, thank you. So I think we should stop now. There are still some unanswered questions in the chat, but you can have them when Dominic will put the video of the seminar plus the chat on the COMSOC video seminar webpage. So I think we thank you all again for the last time.
Thank you for listening.
And as I told you, we will be back in 2 weeks from now, 1 hour later than usual, with Roman Spanks and Jody Masso. So have a great weekend for everybody.
Okay, so now I will check out the chats, and yeah, if you have any question, just you can also just directly tell me.
No, that's not fine. You're not answering, you're not making quick answers, Peter, I must say.
Okay, so
the impression we have is that you want really to talk as if you were locked down or something like that. You know?
Okay, so who needs a T-shirt? I'm just checking. So
I don't know.
Harris.
I think I have one somewhere. So I guess.
Can I just give one comment? And I want a reference. In fact, your dog. So the woman likes the man, who likes the dog, who likes the woman. This example, I remember with the Jose Rafael Correa. He was in Paris, visited me in Lamsad, and we spent 2 weeks trying to solve this problem. We defined the problem and we tried to solve it. We didn't solve it. So I didn't know that it was stated formally in, because we started we tried to do matching with 3 people, and then we arrived to this as something where perhaps it may exist, but we didn't succeed to find the example, counterexample. Then Jose left and we didn't work on it at all after. So I'm happy that you solved it. So if perhaps you can send me the paper for that.
Yeah, sure. So this was this COMSOC paper, 2008, where we had this counterexample, but the published journal version is from Algorithmica 2000.